So we're going to be back right on schedule. So it's a few seconds before 2:30 p.m. And it's a great pleasure to introduce the first afternoon speaker, which is Luca Iliesiu, who will explain us something about the factorization of the Hilbert space for the two-sided black hole. Take it away.
Oh, can we put the slides up? Great. Thank you very much for the invitation to this fantastic conference. So today I'll tell you a little bit about how the Hilbert space of two-sided black hole factorizes. And this is work that I've done together with 3 graduate students, all of them amazing, Jan Boruch, Wanda Lin, and Cynthia Yan. And at the end of the talk, I'll also give a teaser for some related work that I've done with these collaborators. Let me introduce what the problem with the Hilbert space of two-sided black holes actually is. So let's consider the Hilbert space of two-sided black holes in ADS CFT. So according to ER equals EPR, the Hilbert space that the states of two-sided black holes belong to is a tensor product between the left Hilbert space of the left boundary and the right Hilbert space of the right boundary. So this is a boundary, a purely CFT perspective. However, one can try to understand whether this statement is true by quantizing the bulk, at least perturbatively in G Newton. So to do that, we can specify some gauge fixing conditions to fix a slice that connects the two boundaries and specify the induced metric and the wave function of matter fields on that slice. And the issue is that the bulk Hilbert space that we get in a 1 over G Newton expansion seems very different than the tensor product of two Hilbert spaces, the left and right Hilbert space. And I'll prove why that is in a few slides. So the simplest example that you could come up with, and this will be my focus of the talk, is in JT gravity coupled to matter. JT gravity, as most of you probably know, is a two-dimensional dilaton theory that we can couple to matter. So there we can describe the perturbative Hilbert space very precisely. States are described in terms of 2 parameters, the length of the Einstein-Rosen bridge in between the 2 sides of a two-sided black hole, and the matter wave function on a slice, which is parametrized by the matter Hilbert space. And because JT gravity is a rigid theory, it just describes a patch of ADS2, the matter Hilbert space can be decomposed into unitary representations of the universal cover of SL2R. So states here are labeled by length, delta, and m, where delta and m parameterize the unitary representations of SL2R. Of course, you see from this form of the perturbative Hilbert space that it's nowhere near close to factorizing into a tensor product of left and right. And you could even try to choose a different choice of basis to describe these slices. You could indeed describe states in terms of the left energy, the right energy. But in addition to the left and right energy, you still have to specify something about the wave function of matter fields on a slice. So you still have to specify the irreducible SL2R representation that these states belong to. And just from this form of the state, you can see that the states themselves are not just labeled by a left and right energy. They just have more labels that cannot be probed by looking at only one boundary. OK, so the fact that the Hilbert space of two-sided black holes seems different than the factorized boundary Hilbert space, it's what's known as the factorization puzzle. And this puzzle I'll denote with the British S. Good. And it was often thought that resolving this puzzle requires a detailed knowledge about the UV completion of the quantum gravity theory that we're discussing. But in this talk, I'll actually propose a resolution to this puzzle using simply the tools of low-energy effective field theory. So namely, I'll show that non-perturbative effects are what resolve this puzzle. Namely, we will prove that H bulk is indeed equal to H left tensor H right after taking into account these non-perturbative effects. But before I go into this talk, I want to give a little disclaimer, since I know some people might be confused, this puzzle about the Hilbert space factorizing is different than what's known as the factorization puzzle with a Z, which talks about the partition function, multi-boundary partition function, factorizing into a product of partition functions. So the two puzzles are different, and in fact, the non-perturbative wormholes that give rise to the factorization puzzle with the Z will be able to restore the factorization puzzle with an S. And I'll comment more on that later. Okay, so another way to describe, another motivation for describing the lack of factorization comes from the algebraic classification of gravitational observables on one side of the two-sided black hole. So let's consider one side, let's say the left side, of a two-sided black hole. And let's try to describe what the algebra of observables in this subregion is. Well, there's three levels of approximation that we can make. The first is if we turn off G Newton completely. In this case, we just have the matter, the QFT, on a black hole background. And it's known that if I take some subregion of a quantum field theory, the algebra of observables is a type 3 von Neumann algebra. And familiar notions that we're usually used to in quantum mechanics are not well defined. Density matrices, traces, pure states, entropies, nothing like that is well defined. Now, if we turn on G Newton a little bit, so if we couple the matter to gravity, it turns out that the algebra switches from type 3 to from type 2. In a large number of examples, at least, this happens. And familiar notions become better defined, but there is still no pure states. And I believe you'll hear more about that tomorrow. Now, this is in slight contradiction with what we know when G Newton is finite. When G Newton is finite, according to ADS CFT, since the Hilbert space factorizes into a tensor product of Hilbert spaces, we should be able to define pure one-sided states. And that's in fact the requirement for a type 1 algebra. If we show that there are pure one-sided states, we get the type 1 algebra. So essentially proving factorization will help us understand how the algebra transitions from a type 2 to a type 1 von Neumann algebra. So what's the strategy? The strategy is to use the gravitational path integral to prove that if I define a trace on the bulk Hilbert space, on the Hilbert space that's spanned by the states of the two-sided black hole, for any operators in the left and right algebra, the trace factorizes into a product of traces. And this is actually sufficient in order to prove that the Hilbert space itself factorizes. And in this talk, I'll only focus on a subset of operators in this algebra. It's a sufficiently generic subset to still guarantee factorization, but in principle, one can discuss a more general set of operators. I'll take k left and k right to be exponentials of the left Hamiltonian and the right Hamiltonian with arbitrary inverse temperatures, beta left and beta right. So, the fact that this trace factorizes just amounts to saying that this trace is a product of a function of beta left, this one, times a function of beta right. So before I discuss more about this strategy, I have to first define what this H bulk is, right? In the previous slide, we have to take a trace over the two-sided Hilbert space. So I have to describe how do we construct this two-sided Hilbert space. To have a hope of seeing factorization, we need to break the gauge constraint that the left and right energies are equal. So for instance, in the thermal field double, there's a constraint, right? That the left and right energies are equal. And if we only take states for which the left and right energies are equal, there's no possible linear way in which I could get all states in a factorizing Hilbert space. So in order to do that, you actually need matter fields. So the way in which we will construct H bulk is we'll take states that make semi-classical sense. They're like the thermal field double states where I consider some matter operator insertions. And I evolve this matter insertion by beta over 2 to the left and to the right. And for convenience, I'll work in a finite dimensional Hilbert space where I'll restrict the energies on the left and right side to just belong to some arbitrarily large energy interval. And I can construct a Hilbert space that is the span of states constructing with different matter operators. these different matter operators perturbatively can give orthogonal states. For simplicity, even though in the paper we prove a more general statement, for simplicity I'll restrict to the case where the masses of all these matter operators are approximately equal. And the states that one can construct in this way are typically also known as bag of gold states, because from the outside, if I continue these geometries to the Lorentzian signature, these geometries look the same regardless of what this operator insertion OI is. The important thing, though, is that this operator insertion now breaks the constraint that h left is equal to h right. So at least we have a hope of seeing factorization for this Hilbert space. So in order to calculate trace h bulk, we can expand trace h bulk in terms of the basis of states qi, regardless of whether the basis of states qi is orthogonal or not. Namely, for any set of states qi, right, whose span gives h bulk, this is the formula for the trace, where this M is the Gram matrix, is the matrix of overlaps between these states qi, and this is a generalized inverse. So this is the unique formula for the trace in the two-sided Hilbert space. And the strategy will be to try to compute as much as possible about the statistics of these trace and check that it factorizes. And what do I mean? What do I mean to compute the statistics of these traces? Well, I mean that even though we cannot compute these individual inner products that appear in M or appear in this factor, we can compute their statistics by using the gravitational path integral when accounting for space-time wormholes. So for instance, if instead of just computing the statistics of qi qj, I compute the statistics of qi qj squared, there's two possible contributions that I could take into account, or sorry, a series of possible contributions to take into account. The leading contribution comes from disks, or ordinary black hole geometries. And the first subleading contribution comes from a wormhole geometry that connects the two inner products. And in JT gravity, these geometries are weighed by e to the s naught times the Euler characteristic. So this geometry is weighed by e to the 2s naught. Each one of these is weighed by e to the s naught. And this geometry is order 1. So in principle, this correction is small. But it turns out if I consider enough states in h bulk, the correction to the trace due to these wormholes can become very large. And I want to point out just a sociological thing, that the fact that we're computing non-trivial statistics for overlaps doesn't necessarily point to the fact that we're in an ensemble average theory, even though in JT maybe we have an ensemble average. But perhaps the better interpretation is that we're doing some coarse graining of a regular UV complete theory. And this is what these wormholes capture. OK? So using this assumption, we can compute trace h bulk by using the replica trick, writing the matrix M to the power n, and analytically continuing n to -1. So in general, there's multiple geometries contributing to this. So here, the blue dotted lines represent contractions between the different possible indices of the operators that appeared on these wormhole geometries. And in addition to that, we need to insert the operator k left and k right, which were e to the minus beta left h left and b to the minus beta right h right on some boundary. And this specifies a set of boundary conditions that we can now fill in. We want to see what all the possible gravitational solutions that satisfy these boundary conditions are. Now, the leading geometry in e to the s naught is just the fully disconnected geometry, right? It's just multiple copies of the Euclidean black hole geometry, so multiple copies of the disk geometry, where the only possibility is that all operators that appear here, right, that generates these states qi, are all the same. So this geometry is a leading geometry in e to the s naught. And if we only take this geometry into account, we would never see factorization. And this is kind of clear because I can explicitly write the trace over the perturbative Hilbert space as a sum from 1 over k. These states are orthogonal to each other, so the matrix M is just trivial, it's just the identity. of the inner product between qi, k left, k right, and qi. And this sum just grows forever, right? The more I increase k, the bigger the trace is. So there's no chance of seeing that at some point, if I include more and more states, eventually this perturbative trace will diverge and will stop making sense. There's no sense in which it will start factorizing. So this verifies that perturbatively we never see the Hilbert space, that the Hilbert space factorizes. And this is because when I take k to be large enough, when k is large enough in this sum, when it's of order, when it competes with e to the 2s naught, we cannot ignore subleading corrections in e to the minus s naught. And this can be seen by comparing two contributions, the fully disconnected contribution that we've seen earlier, and the fully connected contribution, which is suppressed by factors of e to the s naught. So this, the Euler characteristic of this disconnected 4 surface gives e to the 4s naught, and the Euler characteristic of this surface gives e to the minus 2s naught. But the factors of k that come from the index contraction is different in such a way that these two things become competitive precisely when k is of order e to the 2s naught. So to prove factorizations, we need to resum all wormhole geometries in a double scaling limit. In the scaling limit where the number of states in the Hilbert space scales with e to the 1 over g Newton, or with e to the s naught. And in the limit in which we take all these parameters to be large. So we'll prove factorization in multiple steps. First, we'll prove factorization to leading order in g Newton. So this will be probably the most important step of the talk, what I'll be focusing on. So we'll prove that the trace in question factorizes into a product of traces when the number of states that I use in the span of h bulk is bigger than the expected dimension of the Hilbert space of two-sided black holes that you get from the Gibbons-Hawking prescription. So this factor of d is roughly speaking e to the entropy of the black hole. Now, when k is smaller than d squared, I don't have a complete set of states, and the answer that I get is a complicated non-factorizing answer. So the nice thing, though, is that even though we're probing statistics, we can go beyond leading order and probe factorization exactly. So what do I mean by that? Well, imagine that we study subleading contributions in e to the s naught. Well, the problem is that we would need to also probe some correlations between the left energies and the right energies. So the trace itself, the trace over h bulk of k, will not necessarily factorize into a function of beta left and beta right at subleading order. However, observables that vanish, any observable that vanishes in a factorizing theory, should also vanish once I take the coarse graining of the theory. So for this, let's define the following differential. That's a function of beta left and beta right. It's just the derivative with respect to beta left and beta right of the logarithm of the trace. So if this trace factorizes into a function of beta left and beta right, then the log is just the sum of two terms. And if I take a derivative with beta left and then a derivative with beta right, this should vanish. So the vanishing of this differential precisely probes that the bulk Hilbert space is the tensor product of left and right. And this holds if the eigenenergies of the Hamiltonian are non-degenerate. And I'll discuss counterexamples and how to deal with them at the end of the talk. So what we'll manage to show, and I won't focus on this as much today, feel free to ask me afterwards, what we'll manage to show to all orders in 1 over g Newton and to all orders in e to the s naught is that this differential vanishes on average, and this differential squared vanishes on average. So if you have these two statements be true at the same time, then the only option is that this differential vanishes even before coarse graining. Right? If you're taking the statistics of a quantity that's real and its average vanishes and its square exactly vanishes, it means that it vanishes either in all members over the ensemble or before coarse graining. So today I will mostly be focusing on step 1, though. So to compute the trace, we need to resum all the possible geometries that are filled in by these boundary conditions. And it's well known from calculations of the page curve that in order to do that, it's convenient to define the resolvent for the matrix of overlaps M. So the resolvent is just 1 over lambda minus M. And the nice thing about defining the resolvent is that using the resolvent, I can actually compute what the trace itself is, right? So remember that the trace is just the limit when n goes to -1 of this quantity. So in principle, it's just the integral of d lambda over lambda of this factor. So the advantage of using the resolvent is that I can expand the resolvent in a geometric series. I get multiple contributions coming from disconnected geometries, right? The leading, at leading order in the geometric expansion of the resolvent, there's no power of m. Leading order, there's 1 power of m. Then there's a power of m squared that gets 2 contributions, one from a disconnected geometry and one from a connected geometry, and so on and so forth. But the nice thing is that this geometric series arranges itself in terms of a Schwinger-Dyson equation where the resolvent appears on both the left and the right sides. Now, the resolvent multiplied by the inner product, the matrix element of k left and k right that I need in order to compute the trace, can also be expressed in terms of a Schwinger-Dyson equation where on the right-hand side of the equation, the resolvent itself appears. So while these equations can be expressed in images nicely, they also take a nice form in equation form, where on the left-hand side I have the resolvent, and on the right-hand side I have an integral of a function that involves the resolvent, and the matrix elements appearing for the operators on each boundary. And similarly, the trace of H bulk can also be similarly expressed in terms of the resolvent and the matrix elements appearing on each boundary, where the only difference is that one of the matrix elements is multiplied by the additional factors of k left and k right that we've inserted. So it's multiplied by e to the minus beta left, e left, e to the minus beta right, e right. Now, in principle, we are just tasked with solving this equation, finding the resolvent, and plugging it into the second equation, and that gives us the trace for any value of k. However, we cannot actually solve the Schwinger-Dyson equation exactly. Instead, we can just constrain its analytic structure. So it turns out that the resolvent, we can prove that the resolvent only has a branch cut on the positive real axis, and a possible pole at lambda equals 0. And we can also constrain what the residue at the positive of this possible pole is. This possible pole only exists when k is bigger than d squared, and its residue turns out to be k minus d squared. Now, the fact that the resolvent only has non-analyticities on the positive real axis implies that the Gram matrix is positive semi-definite, which implies that we have a semi-positive definite inner product, even non-perturbatively, even when we account for these non-perturbative corrections. Now, this pole that we see in the resolvent turns out to be very powerful. This pole, for instance, determines what the dimension of the Hilbert space is. A pole in the resolvent implies that the matrix of overlap has 0 eigenvalues. And the matrix of overlaps having 0 eigenvalues implies that the set of states Qi is linearly dependent, and there exist linear combinations that vanish, so-called null states. So this implies that the dimension of H bulk is precisely d squared, which is what we expected and what people have previously seen in the page curve. But the non-analytic structure for the resolvent also allows us to do more. It allows us to compute the trace itself and check factorization. And this is very simple once you realize that to compute the trace, in principle, you need to compute this contour integral over all the positive poles of the resolvent. But you can simply deform this contour to only pick up the contribution from the pole or no pole at lambda equals 0. If there's no pole at lambda equals 0, you pick up this pole of this function that appears in the formula for the trace. So there's 2 options. If R has no pole, this implies that there's no null states. And here you can just compute this integral exactly, and you get an ugly non-factorizing answer. You could almost see it from where you are. Yeah, 2 minutes. Good. You just get that this R of lambda is replaced by an R0, and the overall answer just depends on beta left and beta right in a very complicated way. However, if R of lambda has a pole, notice that if we're only picking up the contribution of the pole, these two factors cancel, and we're just left with the ratio of matrix elements that appeared in the resolvent when we inserted k left and k right, and we did it when we didn't insert k left and k right. And the ratio of the two is precisely e to the minus beta left times e to the minus beta right. And when you integrate against these two factors of the density of states, you get the product of two partition functions, which is exactly the factorizing answer. So the physical mechanism for factorization is the following. Poles in the resolvent imply null states, which in turn implies that we've constructed an over-complete set of states. And precisely at that point, we see that the trace factorizes. And you could see this very nicely in this plot, where I plotted the trace as a function of k. And you could see that eventually it plateaus precisely at a factorizing value. Or you could see it by looking at the differential that I talked about at the beginning of the talk and seeing that it vanishes precisely when k is equal to d squared. And before that, it takes a non-zero value. So if you want, this is like the page curve for factorization. This plot is a consistency check, consistency condition that eventually, once we have a large enough number of states, we see a factorizing Hilbert space. And we can, as I said, we can do this to all orders to prove that products of traces also factorize. And this implies that the differential that I showed at the beginning of the talk to the nth power is on average 0. So at large enough k, this we can do at large enough k. So at large enough k, we could show that this differential is 0 to all orders. Okay, so even despite only having access to statistics, we can now prove that factorization occurs exactly even before coarse graining. So that's the upshot of the talk. So since I'm out of time, I'll just leave you with some final comments. The fact that the trace factorizes implies is satisfies the requirement for a type 1 algebra. The first step in my computation only involves saddle points of the Euclidean path integral, and this means that, this has led to a generalization of what I showed to higher dimensions by VJ and company. The third point addresses a point that Lenny brought up earlier this morning. What if the bulk has a gauge symmetry and the boundary has a global symmetry? What happens in that case? There is a degeneracy of eigenvalues, and in order to see factorization, we also have to turn on a chemical potential for the charges associated to that global symmetry, and we still see factorization, but that happens if and only if we have particles in all irreducible representations of the gauge group. And similarly, in the case in which there's a degeneracy due to supersymmetry, like when we have BPS states, two-sided BPS black hole states, we can similarly see that the trace of an arbitrary simple operator factorizes into a product of traces once k is bigger than the dimension squared. Okay, I'll leave it at that. Thank you very much.
Thanks. Are there any questions?
Oh, I see a question all the way in the back.
Oh yeah, over there.
Yeah.
Get a microphone over there.
How you get, yes. So for instance, you can get, it's a bit complicated, but for instance, you can get the pole by plugging in that value of the pole, by plugging in that ansatz for the pole and its residue in the Schwinger-Dyson equation, and that solves for the residue. And similarly, you can try to solve for the location of the branch cuts by demanding that that the derivative of the function at the derivative of the resolvent at the location of the branch cuts vanishes. And yeah, that sets the only possible way to satisfy that equation is for lambda plus and lambda minus positive. So we checked poles and all branch cuts. And yeah, just to summarize again, we only found poles at lambda equals 0 and branch cuts whose ends are on the positive real axis.
It's a question of Daniel.
Hey, so yeah, about this issue of to what extent it depends on the UV. So if I wanted to know what does a product pure state look like in the bulk, don't I need to know what black hole microstates are or something like this?
Yes, so you mean if you wanted to write down the specific linear combination of these states Qi that gives you a product pure state, right? The coefficients in that linear combination depends on the detail of the UV. Completely agreed with that. However, the proof that factorization occurs can be made even without finding those coefficients explicitly, right?
But yeah, so I think that's, you can say you showed that the path integral is consistent with the hypothesis that, you know, there's some ensemble of state theories that factorize or something like that, right?
Or that it factorizes before coarse graining, yes. It depends on your perspective on wormholes. One perspective is that they come from an ensemble average. The other is that they capture the statistics of underlying quantities in the UV complete theory. So for instance, they can capture the statistics of energies, of OPE coefficients, so on and so forth.
Yeah, but probably the details depend on, you know, which compactification of string theory. You know, if you actually want to know what the states look like, right? That where you know, the products.
Yeah. If you want to find the exact coefficients in the linear combination, yes, you do need the UV completion. But if you just want to prove that the theory factorizes, you don't need to find those coefficients, right? You know, an example of that is ETH, right? The coefficients in ETH, of course, depend on the UV completion. But we can make the statement of ETH even without knowing the UV completion of the theory. Like in whatever compactification you want, presumably if you go to high enough energies in a sector without supersymmetry, some version of ETH is satisfied. And I would say that this is analogous.
I think it's the same as with black hole microstates. You can learn about the number doing the path integral, but if you actually want to know what they are, that's different.
Sure. Well, this is a basis of you know, black hole states. You could choose a different basis if you don't like this basis, but yeah, I don't have more to say about that. The only thing about this basis is that it makes sense semi-classically, right? All the states in this basis make sense semi-classically.
We'll take 2 more questions. I see Sufrat, and there's another question in the back there. If I see, yeah. And then we'll move on to the next one.
So I'm actually just going to rephrase the previous question slightly differently. So let's say, you know, this trace of the square of that you were computing, you know, this is sensitive in principle to UV effects, right? And to get 0 is actually, you know, it's not like you're getting a big number which could be corrected. You really want to get 0. And if that 0 was corrected by alpha prime corrections, which you wouldn't see in your computation, then that would spoil factorization once again, right? So isn't there some...
You mean if I computed the alpha prime corrections on top of these
yeah, for instance, yeah. So you, instead of getting 0, you might have got something that was non-zero, and that would have spoiled factorization. And so isn't there something to be concerned? I agree what you've shown is that the path integral is consistent with factorization. But
yeah, so I've only taken into account, I've only taken into account non-perturbative effects in G Newton. You could be concerned about alpha prime corrections, and I don't have much to say about that.
These are much larger, of course, in magnitude than these non-perturbative effects. Because they're not, you know, they're not e to the -1 over G Newton.
I agree, but maybe let me just comment that in this formula for, you would expect this structure for the resolvent itself to take the same form. And the only thing that I believe would receive alpha prime corrections are the density of states and the matrix elements or OPE coefficients of the operators that you've inserted. And notice that here, in the reason why factorization occurs is just because the ratio of matrix elements when you inserted k left and k right and when you didn't insert k left and k right ended up being independent of the OPE coefficients. So there's a lot of universality to the way in which this formula is derived, that it's basically insensitive to the exact values of the OPE coefficients of the operators involved in the creation of these states. And even if here the OPE coefficients receive alpha prime corrections and the density of states receives alpha prime corrections, you would still see the same mechanism for factorization.
Okay, thank you.
Last question. Yep.
I can hear you.
Yeah, so my question is, in which sense the factorization of the two-point function implies the factorization of the Hilbert space? Because I agree that if it's the other way around, then it holds, but I'm not sure whether the factorization of the trace implies Hilbert
we can
space
discuss this
factorization.
after, but if you have an operator that doesn't have degenerate eigenvalues on the Hilbert space, then you could show that it implies the factorization of the Hilbert space. And then you have to deal with the cases in which the Hamiltonian has degenerate eigenvalues, and that's why I had these comments on this final slide, that you could do the same in the case when there's a global symmetry, right? When there's a global symmetry, you might expect that there's some degeneracy of eigenvalues, and you could resolve that by not only looking at the Hamiltonian, but also adding charges. Or you could do the same thing in the case of BPS operators. BPS operators have all the same energies, right? So they cannot be distinguished by the action of the Hamiltonian. For that, we had to use some simple operator that has a non-trivial action on BPS states. So as long as your operator doesn't have degenerate eigenvalues on the Hilbert space, or if it does, as long as you have some way of splitting them, then you can probe the factorization of the Hilbert space.
All right, let's thank Luca again. Next up is Kristan Jensen, who will talk about non-perturbative JT de Sitter gravity.
Should I give him the...
That's a great question. I think so.
Good. Oh, you are? I am good. Oh, excellent. Okay. Well, thank you very much for the invitation. It's lovely to be here. It's an honor. Today I'll be talking about some work with Jordan Kotler, a paper that appeared last year after several years of effort of thinking about the de Sitter version of JT gravity. Now, this is the first of several talks this conference about de Sitter quantum gravity, so I feel obliged to just mention at the outset that many basic features of de Sitter gravity are less explored than its ADS cousin. And there's a lot of room for exploration both from a more practical point of view. Questions, for instance, like what is the right measure for cosmological correlators encoding non-Gaussianity at the end of the inflationary epoch? There's room for investigation there, as well as on a much more formal ends. Questions like, is de Sitter gravity holographic, and so on, and if so, how? Now, in this talk, I'm going to be studying a spherical Cow approximation to the problem in the form of the de Sitter version of JT gravity. Joukey-Teitelboim gravity, at least its ADS version, has been in vogue in our community for quite some time now as a toy model for various phenomena, including factorization, page curve, and so on in the ADS setting. And, well, there's a de Sitter version of the model, and that's what I'll be focusing on today, with the main goal of being able to discuss transition amplitudes in the theory and understanding its quantum mechanics. I thought I'd begin with a list of some of the major results that I'll flesh out over the course of the talk. we do have a number of results. We also have kind of a framework, a way of thinking about the problem, which I hope will be conveyed as the talk goes on. As, again, the problem is a little bit different than the ADS version. The main bullet point on here is the third one, that we arrive at some genus expansion for transition amplitudes, which you can think of as sort of the S matrix of the model. And to do that, we have to make sense of the gravitational path integral in this context. So we have to make sense of sum over r equals 2 metrics, which I'll discuss in some detail. And a line that will take us from beginning to end is to think about all the operations that we're doing in terms of the quantum mechanics that's being described. I'll also comment at the end in what sense what we find is consistent with there being a holographic dual, albeit with scare quotes that I'll explain then. And I should mention maybe, so the title of the talk is Non-perturbative de Sitter gravity. The non-perturbative, from this point of view, refers to the fact that we're able to make sense of a genus expansion at all, which is non-perturbative from the point of view of a sum over metrics. However, because we're still a bit unsure as far as whether there's a dual description or not, we will not be able to comment about physics that are non-perturbative in the genus expansion, or in the string coupling, rather. All right, so I'm going to spend some time setting up the problem. After we do, we'll be able to borrow heavily from technology developed by Saad, Schenker, and Stanford and their solution of ordinary JT. With that in hand, I'll discuss some results and wrap up with some future prospects. This is the old version of the talk. That's interesting. OK. I sent Ahmed a new version earlier today. This doesn't bode well for you, Eric. Sorry. My inhibitions are down due to jet lag. So if we're going to discuss the transition amplitudes in this kind of setting of a theory of gravity, while we're talking about sum over de Sitter metrics, spacetimes that are asymptotically de Sitter, and while in a de Sitter setting, there's a conformal boundary that's space-like rather than time-like, and so the path integral with that kind of boundary condition, what does it do? It prepares a state. And in this talk, the kind of boundary conditions, the kind of states that I'm discussing, are very similar to those of describing nearly ADS geometries in ordinary JT. So in them, the metric is de Sitter at very, very large positive or negative times. So I'm indicating that with some kind of trumpet-like shapes. And then the dilaton of JT is growing. It's becoming very, very large, either in the far future or in the far past. And I call the coefficient, the rate of expansion, big phi, phi plus for the future, phi minus for the past. That's the data with some suitable choice of coordinates. That's the invariant data that labels these boundary conditions. And I can think of that then as labeling the bra that's prepared by the path integral subject to such a boundary condition in the past, or a ket that is prepared with such a boundary condition in the future. So these states are labeled by big phis. And as I'll mention in a little bit, they come with an I epsilon prescription that I'll explain. And these states that I'm describing, I'm going to call them asymptotic states, because they're prepared at asymptotically early or late times. And there's also a footnote here that I'll talk more about by the end. Right, so we have boundary conditions. Now we want to sum over metrics subject to these boundary conditions. And while in de Sitter JT, we're talking about theory of r equals 2 metrics, so we want to sum over r equals 2 metrics with those boundary conditions. However, if you've ever played with these, there's a real paucity of Lorentzian, non-singular r equals 2 metrics. On the cylinder, there's a whole moduli space of them, but even on the disk, there's no such metric. So in general, what we're forced to do if we want to make sense of JT on a general surface, on any topology, is to consider complex time contours. And one thing that will help us as we do so is that on a general, we're going to exploit a trick that's kind of familiar from the going back to Juan's discussions, computations of primordial non-Gaussianity, is that a hyperbolic metric in minus signature has curvature equal to +2 rather than -2. And we're going to include such ingredients as building blocks to form R equals 2 spacetimes, as you'll see on the next slide. Now, the integration domain that we're going to land on over these metrics ends up being the same. It's identical to that of ordinary ADS JT gravity. However, we find that we will also need a different measure, one that's related by a phase in some way that depends on the genus and the number of boundaries of the spacetime to that of ordinary JT gravity, and I'll explain why shortly. So here's a cartoon for the kind of complex time contours that I have in mind in this problem. So down here, time is running from left to right here, or at least real part of time. So I have in mind a process in which I prepare a very, very large universe characterized by some phi in the far past, and then it splits into two universes in the far future. I call phi 1 and phi 2. And asymptotically, the geometry is Lorentzian here and here. But then as I go into the bulk, as I evolve in time, I start deviating in imaginary time, always going down, until my trumpet, I'll call it the same terminology as what we're used to, becomes minus here and here, with some geodesic borders. And then I glue in one of these hyperbolic metrics on pair of pants with geodesic borders. That's my intermediate surface. And with this choice that time is always going down in imaginary time, the Euler term in the JT action gives me the usual kind of string coupling. So this topological expansion that I get is perturbative at large S0. Now, JT is so bloody simple, it only has moduli and edge modes. There's no propagating excitations. And so it may not be a surprise that we can push this complex time contour that I just described to something that's always such that the surface is hyperbolic and minus. I can do that provided that, when I do that, these trumpets become kind of ordinary ADS JT trumpets, albeit in minus signature, but I have to carefully track what happens to the Lorentzian boundary conditions that I started with under such a push. And what ends up happening is that I end up with kind of ordinary trumpets, but where the renormalized dilaton, or the renormalized size of the circle at infinity has been analytically continued to complex values. So it's 1 over I phi if we're preparing a future circle, and minus 1 over I phi if we're preparing a past. And now there's also a little bit of I epsilon that shows up here. So it turned, and I'll explain this shortly here. So we end up finding that I should think of this phi in the future as being equipped with a very small positive imaginary part, a plus I epsilon, and phi in the past with a very small negative I epsilon, which I can think of as saying here that the betas that we continue to are some imaginary part minus a little bit of real. This makes de Sitter JT a bit different. If epsilon was slightly positive, we would say that what we're doing here is we're looking at moments of trace theta of the evolution operator in ordinary JT gravity. And this minus sign makes it different, along with the measure that I discussed earlier. And this has also the added virtue that this I epsilon is really distinguishing between whether our path integral is preparing a bra or a kept. Now, with all those definitions in place, we are in a position to discuss transition amplitudes. We impose boundary conditions in the past and in the future, and then we fill it in with geometry. But at present, and I want to interpret those as matrix elements of an infinite time evolution operator. However, to think of those as real amplitudes, we should pause for a moment and hold up, because to do that, we would need to make sense of these phi's forming a Hilbert space on their own. I should be able to make sense of an inner product of these phi's with themselves. And following some idea that we had a few years ago, we were able to assign such an inner product in terms of another computation, another gravitational path integral, where we sum over very, very thin, tiny strips of space-time that interpolate between asymptotic circles, or asymptotic boundary conditions. And at least for the case where we're talking about states prepared by a single universe in the far future, say, this is the result that we find for that inner product. There's some sign, actually. This is where the measure that I discussed earlier briefly shows up. This sign is positive for the measure that I described previously. So this is kind of, why did we make that choice? We did it so as to have a healthy quantum mechanical interpretation. There's some square root prefactor that comes from an integral over Schwartzian modes associated with each boundary. And then there's a delta function that comes from moduli, because this little cylinder, it's still, even though it's a very short cylinder, it's still topologically a cylinder, and so has moduli to integrate over. Now, once we have that inner product in hand, we can rescale our external states so that they're properly normalized, and now we can talk about normalized transition amplitudes in this theory. There's another thing that we have to do first, though, to finish setting up the problem. De Sitter JT has the analog of the no boundary state, and we're familiar with from higher dimensional gravity. That's prepared by just smooth caps. So, for instance, we would interpret the path integral where there's no past asymptotic region, there's just smooth geometry, and then there's some future regions. We would interpret that as computing the wave function of this no boundary state evolved to the far future in the basis of these asymptotic states. Now, this no boundary state and its evolved version in the far future in De Sitter JT happens to be non-normalizable. And this is different than other settings. So for instance, this is the computation I have in mind here. The norm of the state is is to leading order in genus expansion. It's the sphere partition function of JT, which diverges at one loop. Now, so what we do then is we want to study kind of a constrained problem where we study infinite time evolution. We prepare something in the past, in the far future, but we condition on the statement that we don't want to evolve into this no boundary state or come out of it. And in practice, that means that we want to study matrix elements of an operator that I call mathcal-U, which describes in gravitational terms the problem where we have some boundary conditions in the past, some boundary conditions in the future, and we demand that space-time smoothly interpolates. It smoothly connects past to future without capping off. And that forms our dictionary that we can then study. So we study this path integral, and then we interpret those as matrix elements of this operator mathcal-U. We can also do the Hartle-Hawking state and so on. I'm strapped for time, so I'm not going to discuss it. So there's some takeaways in this setup that I want to stress. The first one is that we're really integrating over metrics with a complex time contour in this setting, and with a particular measure that generates a phase. That's going to be important for us. And particularly, it leads to a healthy quantum mechanical interpretation. This path integral, what we claim is that we can give an assignment of inner product of states at infinity, as well as of overlaps between states in the far past and states in the far future. That is, we can even make sense of this operator mathcal-U. There's also this business about Ni epsilon prescription, and I also mentioned that this no boundary state is in this setting not normalizable, which is different from how it usually is in perturbative gravity. Okay, let's get some results from this. So the simplest geometry that we can describe that connects past to future is a cylinder. And well, here we're fortunate. The cylinder is a classical saddle of De Sitter JT. And we can directly compute the path integral over metrics on the Lorentzian cylinder, either directly in Lorentzian signature, or I can think of it as a sum over minus minus double trumpets. And we, of course, get identical answers in both cases. If I think about it as a sum over Lorentzian cylinders, then this is what the geometry looks like. And our moduli are this alpha parameter here, which is like a size of the bottleneck of the cylinder, as well as a twist that relatively rotates say, the past relative to the future. And OK, now I can justify our I epsilon prescription. We find that this moduli space integral over alpha tau converges only with the I epsilon prescription that we chose. And the normalized version of the result that we get is this one right here. So phi is labeling our past, phi prime is our future, and the infinite time evolution operator as this matrix element. It's 1 over difference of phi's. That thing has a pole when the phi's are equal to each other, and that's nothing more than just the global de Sitter saddle of the theory. Now, of course, we can go beyond the cylinder. We've set up machinery where implicitly we're drawing heavily on knowledge of the space of r equals -2 metrics. We can study it on any surface that we want. But to understand the quantum mechanics of that, it's helpful to introduce one more step. We can slice and dice the cylinder, cutting it in half, and thereby giving us a couple of trumpets, a past trumpet and a future trumpet, as well as some state at intermediate time. And these states are labeled by the size of the Lorentzian bottleneck that I'm calling here big P, which better be positive. And I can think of the cylinder amplitude as some matrix element of this operator. I'm calling it here V dagger, corresponding to the past trumpet, V, its future. And there's some, I can think of these trumpets as computing matrix elements of this V operator between a bottleneck state and then an asymptotic one. And it ends up just looking like the usual relation between overlaps of position and momentum in ordinary quantum mechanics. And where, to leading order in genus anyway, because we're talking about the cylinder, the overlap of these p's with themselves is just delta function. Incidentally, from this point of view, I can describe the wave function of the no boundary state in this p basis. It ends up being delta function normalized to when this p is 1, which, OK, that's one way of thinking about this state being non-normalizable. I'll return to that basis in a moment. But before doing so, let me make a comment. This cylinder amplitude that we just discussed, it encodes something very interesting physically. It's very useful to go to the conjugate variable to this phi operator. Yeah, OK. In the canonical conjugate variable, u becomes just a theta function to leading order in genus expansion. You may recognize this if you stare at this for a little bit. This is just a Fourier transform of the theta function. So in fact, that statement is true to leading order in topological expansion with any number of circles in past and future. If I think of this operator in the cylinder approximation, what is it? It's just a theta function saying that all these p's better be positive. Theta notably is 1 for p positive. P negative, we can understand what's going on here, the fact that the evolution is 0. Those boundary conditions prepare states described by geometries that crunch, that develop a singularity. And when we sum over non-singular metrics, such configurations are projected out. So another way of saying it is that the path integral is naturally restricting us to those states where the space-time remains macroscopic. It doesn't crunch with this choice. Now we're in a position to then discuss the more general problem, where we have a state with m circles in the past and in the future. Ends up being some moduli space integral. Time is limited, so I'll flash what happens if we go to this conjugate basis. Instead of fixed phi, it's conjugate p, in which case this amplitude, what does it become? it becomes a Weil-Petersen volume, but analytically continued in its arguments, and times some genus-dependent prefactor that comes from this measure that I mentioned previously, plus the constraint that all these p's better be positive. Now, this allows us to kind of decompose the amplitudes that we find in an interesting way. We can think of this infinite time evolution operator as basically a pass trumpet, and then an effect that comes in from gluing in this intermediate surface, and then a future one, a future trumpet. And where to leading order in genus expansion, or rather these trumpets don't get corrected to any order, but the intermediate surface you can think of as kind of telling us how we glue a bra to a ket, and that receives corrections in genus expansion. I'm going to skip that slide because I got deleted in the next version. Now, in what sense does any of this have to do with a holographic dual? What I described in this talk was just a direct gravitational path integral where we exploit the existence of R equals of hyperbolic metrics, but in minus signature. But it turns out that the end result that we find, it can be understood after the fact as just some analytic continuation of ADS JT amplitudes. And that continuation is a combination of two steps. You continue S naught, which has the effect of taking the string coupling and putting an I in front of it, as well as continuing beta, as I mentioned, from having positive real part to negative. And the first one, what it does, that effectively turns the genus expansion into an alternating series. And the second thing has the effect that, if we think about inverse Laplace transform, the amplitudes we find they're supported along negative energies instead of positive ones. And it turns out that after a suitable integral transform, these amplitudes that we get, they obey topological recursion, which is a non-trivial statement, but with a spectral curve that's effectively analytic continuation of the usual ADS-JT spectral curve, sinh of square root. And another way of saying this is that our problem really boils down to a certain analytic continuation of ADS-JT gravity. And it's natural then to wonder whether or not there is a sense in which there is a real matrix model dual to everything that I described, a stronger statement than simply these amplitudes are the analytic continuation of the genus expansion of the ADS-JT model. And if such a thing actually exists, the density of states that one would infer from the bulk is not positive. It's oscillatory. It's sine of square root of minus e instead of something that's always positive definite. And we're not quite sure yet. This is why there's scare quotes around this business of holographic dual, whether or not this might come from a matrix integral, but with a complex potential rather than a real one. Now, mention a couple last things. OK. So indeed, to ask questions about this model that are non-perturbative in the effective string coupling, we need to go beyond a topological expansion. We need to know if there's really a matrix dual or not. We don't know at the present time. One thing that gives me some encouragement is that the continuation that we land on, this thing of string coupling and of betas, that's something that we can perform on other matrix models where we do have more non-perturbative control. For instance, we can perform it for topological gravity, which, just the Gaussian unitary ensemble. And in that context, it turns out that if I perform this continuation in string coupling to the GUE, it just maps it to another version of the GUE where the density of states goes from being approximately square root e to square root of minus e. The spectrum gets flipped, and it turns one matrix model into another. And this is particularly resonant with probing the model with trace e to the minus beta h, but where beta is negative. Does something like this happen in JT or not? Is there some sense that we can we make sense of such a continuation? We don't know. One reason why something that is also on the mind, maybe there's some relation to recent work of Scott Collier, Lorenz Eberhardt, Beatrix Mühlmann, and Victor Rodriguez, They had wrote a paper recently about something they dubbed complex Liouville string. This is a variant of minimal string where there's two copies of Liouville theory at central charge 13 plus and minus I large, coupled to world sheet gravity. And this model ends up, they argue it has a 2D target space interpretation as a dilaton gravity with a sign potential that has ADS saddle points as well as de Sitter ones at the roots alternating as you could scan through the roots of sign. Basically because sign near a root behaves linearly and then it looks like JT. They argue further that this has some two-matrix model dual, albeit with an oscillatory density of states. And I do wonder, are these constructions related? There's enough things that sound similar. Can we think of this model as a UV completion of the de Sitter JT that I've been discussing so far? Lastly, I had a footnote earlier talking about other states that can be prepared by the path integral. So recently, Dan Harlow and friends, and then also Jesse Held and Henry Maxfield, wrote a couple papers this fall in which they identified new classical saddles of de Sitter JT, but where the asymptotic dilaton is this is the last slide, where it has roots, where it oscillates. And these are just not considered at all in the analysis that I described. And I think that the physics of these boundary conditions is something that is a nice avenue for exploration. So for instance, in the paper of Daniel and friends, they are able to propose a canonical quantization of phase space of de Sitter JT, including configurations with these boundary conditions. And you might wonder, does that quantization agree with path integral? To test that, you need to make sense of the path integral with these kinds of boundary conditions, which takes you into territory where you have new kinds of Schwarzian models, as pointed out by Jesse and Henry, which are related to kind of exotic coadjoint orbits of Virasoro group. And with that, I will end, and thank you all very much for your attention.
Thanks, Kristan. Questions?
Hi, Christian. I didn't quite understand some of your comments about holography. I thought, going back to the work of Maldacena and collaborators, that at least for the Hartle-Hawking state, say, if you were computing the multi-boundary amplitudes, you could obtain them by taking the South-Schenker-Stanford matrix model, but then computing a partition function, multi-partition function correlators where the temperatures were imaginary, plus or minus I. And isn't that true, firstly? And are you suggesting a different kind of matrix than as a hologram?
That's right. So so there's some history in this line of work. There's a number of papers. I mean, even we have been making some attempt at this problem over the years. So the statements, well, what is new in what I described and what's different than what was written down then? Well, one thing that's different is that, so what you just described is really an analytic continuation in betas, if you will, from the ADS problem. Right. Where's that slide? Here's that slide. So there's two ingredients, there's where beta is taken to be imaginary. There's two aspects of this, though, that we're missing in these papers of 2019. One is like, well, beta should still have a little bit of real part, or at least you need to specify how you're taking the continuation to, the ADS amplitudes are defined on some two-covered sheet of beta. You have to say how you're performing the continuation. So this ingredient, the fact that this I epsilon is not the kind that you would expect from ADS JT, that's new. And then the other thing is this business with phase in the measure of the gravitational path integral, which for, what was the reason that justified this again? It was so that we had a quantum mechanical interpretation of inner product with a plus sign, so that we have a positive norm on states.
Sorry, just say the other, so this came because you chose the measure in a somewhat careful way.
That's right. Yeah, careful treatment of measure, and that filters down. So the thing with this measure, it's a genus-dependent thing. So any one space, it doesn't matter so much. But when you ask the question, is there a holographic dual or not, when you're summing over these things, well, now this choice of measure, it leads to alternating signs in genus expansion rather than the ordinary sum. And that changes quite drastically the nature of the topological expansions. That was the statement that I made earlier that, where is it? If I think of arriving at these amplitudes as continuation from ADS, I have to analytically continue the string coupling as well. And I had a comment on a new version of the slide where, what is the number of effective degrees of freedom in a double-scaled matrix model? You can think of it as e to the 2 s naught. Yeah. What is this thing doing? It's flipping it from being large and positive to large and negative. Does that make sense as a bona fide matrix model is unclear.
Thank you.
Yep, super.
So a lot of what you described seemed very general. So what do you expect something will change qualitatively if one were to add matter to the JT theory and have real local degrees of freedom? Or do you think a lot of the story, I mean, maybe not this slide, but a lot of the story before that would just
No, I'm trying to, okay, maybe I'm sounding more tentative than I feel, but I'm trying to be very careful with especially there's been various fits and starts over the years with this kind of work. It's very subtle. It's very subtle. With matter, I think, let's see. What will change? I mean, all the details, of course, are going to change. I would like to stress, though, that the framework that we're trying to develop, where you make sense of an inner product at asymptotia, as well as the infinite time amplitudes, I think that will survive. It's just going to be more intricate. Is there a role in life for these excursions in imaginary time? Yes, absolutely, as well. Should there be careful attention paid to measure so as to have healthy quantum mechanics? That as well, yes. But of course, all the details will be very different.
Last question.
I think we'll be able to hear you.
Thank you. Yeah. So you were commenting on the fact that the holographic dual looks like a matrix theory with negative degrees of freedom, but then you're comparing back to the story of Collier, Mormon, and others, where the central charge is generally complex, right? It goes like 13.
Well, no. The central charge and the effective number of degrees of freedom are not, well, okay, go ahead. You should finish your question.
Yeah, I was just going to say that seems contradictory, right?
So there's the notion of central charge in the world sheet. What's the central charge of the Louisville theory that you're using as a building block? And then there's some effective number of degrees of freedom of the matrix model that's equivalent to this. And those two things are different. So for instance, the matrix model that's involved here is some double, anyway. So I'm referring here to the matrix model notion of number of degrees of freedom.
Thank you.
All right, we should probably move on, so let's thank Kristan again. And the final speaker of this session is Eric Perlmutter, who will describe an analytic language for 2D CFTs.
let's see here. Great. Christian, here's your water. I'm just going to put it here for you in case you get thirsty. Okay. There we go. Great. Let me take the opportunity to thank Ahmed and the other organizers for giving me the opportunity to speak at this lovely, very purple workshop. It's been great so far, and so I hope to reward the organizers with their choice by talking about some work of the past year or so, which is not yet out, should be released soon, which aims to find structural connections between 2D CFTs and analytic number theory. That's the meaning of the word analytic in the title of the talk, which should appear shortly. Great, thank you. Okay, so yes, we'll find some sort of reformulation of certain quantities in 2D CFT in the language of analytic number theory. And so I'll keep the introduction short, only to say that every talk has a letter. So S, Z, M, of course, who could forget M from strings 30 years ago? In this talk, the letter is L. I'll be constructing L-functions for 2D CFTs and arguing that they provide a good language for understanding questions about the discrete spectrum of generic 2D CFTs, and indeed black hole microstates in ADS3 by the usual translation. So one motivation for this is to probe the substructure of black hole microstate spectra in ADS3, and on the CFT side, this ought to involve finding constraints that act solely on the high energy states. And so I am proposing that the language of L-functions is well suited for this and many other things. So here's the outline for the talk. I'll show how every unitary Virasoro CFT can be attached to an L-function with certain properties that are universal. In this context, the random matrix universality of a CFT can be shown to be equivalent to subconvexity of the L-function, which is something I will explain. But not only this, but this sort of new lens through which to look at 2D CFTs allows us to revisit some old problems. And so I'll revisit this question of upper bounding the lightest non-vacuum Virasoro primary in any 2D CFT, which is the main question in the purview of the modular Bootstrap, and give a proof of this sought-after bound, that that quantity is upper bounded by a C over 12 in any such theory at large C. And finally, just some comments about hints of a lattice structure in generic 2D CFTs. Okay. So L-functions. Simply put, an L-function is a Dirichlet series that meromorphically continues to the whole complex plane under a certain type of functional equation and maybe has some other special properties that mathematicians like. So from my point of view, this is a nice starting point. We have a sum over integers of some coefficients a sub n divided by n to the s. And the so-called completed L function, lambda, is given by q to the s over 2 times some so-called gamma factor times L of s. Q is an integer known as the conductor. And this quantity, right, the main defining feature of these things is that, first of all, it has poles at most at 0 and 1, and obeys this functional equation, okay, where I've written in the so-called analytic normalization, where the central line is that real part of s equals a half. Okay. Now, what are some names for some of these quantities here? So this integer q is called the conductor. The gamma factor here, gamma of s, is a product of gamma functions. The degree d of the L function corresponds to how many gamma functions on the right-hand side there are. And these parameters, kappa, are known as the spectral parameters. And in the functional equation, there's a number here, or a phase in general, known as the root number. And the equation relates an L function to its dual L function, which means that in the L series, the coefficients are complex conjugated. A self-dual L function has no bar on the right-hand side. So a bar equals a. Okay. So here's a sampling of some of the terminology here. Of course, you're familiar with the Riemann zeta function, which is a self-dual L function of degree 1 with unit conductor, root number plus 1, and vanishing spectral parameter. And so it obeys this functional equation. That's this so-called Xi function. Now, needless to say, this is an incomplete review of L functions from a physicist's point of view, but let me just mention some things I think are important. So L-functions are often attached to automorphic forms, both holomorphic and anti-holomorphic. That relation essentially being that of a Mellin transform, as shown here. And the Langland's conjecture program is that all L-functions, suitably defined, although rather generally defined, are attached to automorphic forms of one kind or another. Standard L-functions also admit an Euler product, which takes the form of a product over primes, and there's d factors in this product, some parameters here, which guarantees zero free regions and some right half plane, and connects the L-functions to the primes, or more generally to some set of primitives. The most well-studied class of L-functions are the so-called Selberg class, but it's a much wider concept than that, and certain generalizations, you don't have to go very far to find that either the Euler product or, say, the Riemann hypothesis are not applicable. Okay. So generally speaking, mathematicians' definition of L-functions is broadening over time. Okay, so here are some main open problems. We're going to sort of fly through this, but the slides will be online in case you want to have a closer look. So the first, where are the zeros? So the grand Riemann hypothesis, surely you all know this, is that not just for the Riemann zeta function, but for essentially most nice L functions the mathematicians consider, all non-trivial zeros lie on the critical line sigma equals a half, where the notation is that S equals sigma plus IT, and sigma and T are real. Okay. Mathematicians often concern themselves with finding zero-free regions or density estimates on zeros inside this so-called critical strip between 0 and 1. The zeros have been shown to exhibit random matrix statistics to extreme accuracy. They ask questions about how high can you push the lowest zero, which is a very kind of bootstrappy question to ask, and on and on. Just to quote from this excellent chapter of this excellent book by Iwaniec and Kowalski, I find this quote charming. Proving this even for one L function would be an achievement on a historical scale for human beings. So, okay. Duly noted. Good. So a second problem, perhaps slightly less familiar, but takes up a lot of the literature, is the subconvexity problem, which is the question of how L functions grow as you move high on the critical line. And the Lindelof hypothesis is that the growth is slower than any power of t. So here's sort of a brief explanation. If we define this quantity mu of sigma to be basically the power which bounds the L function high in the critical line at large t, then there's what's called the convexity bound, which follows from some complex analysis argument, which is this orange line here. So I'm plotting mu against the real part of S. And on the critical line, mu equals a half is bounded above by d over 4, where d was the degree. Okay. The Lindelof hypothesis is that actually mu is 0, and then what happens, on this half is fixed by the functional equation by what happens on this half. Okay. Note that the best bound for Riemann zeta is 13 over 84, so not even halfway down from a quarter due to Bourgain and 14. Okay, so there's lots of beautiful stuff here, many other problems. The slides will be online, but we should move on to the application to CFT. Okay. Now, we're going to construct L functions for 2D CFTs. Again, I'm working in the generic setting, Virasoro, compact, central charge greater than 1. And so we will study the Virasoro primary partition function. So you take your partition function, you hit it with root y, eta squared, where y is m tau for this talk. And this counts primaries dressed by some root y, and so there's some expansion and exponentials here. So where are the L functions? Unlike for a non-holomorphic cusp form, where each Fourier mode is characterized by a single constant, here it must work differently because at fixed spin there's an infinite set of data characterizing that mode. So what do you do? So you might try to construct the spectral zeta function for the primaries. So sum over the primaries, make the spectral zeta function of d sub delta over delta to the s. But this is badly divergent for all s because of the Carty growth that is onset at large delta. So this isn't a sensible function. But thinking about where Carty comes from, let's instead do the following thing. Take a difference of two primary partition functions with the same light spectra, where light means dimensions less than c minus 1 over 12. Okay. So we take this difference and we demand that they just have support on the heavy spectrum, operators dimension greater than c minus 1 over 12. Okay. Now form the scalar zeta function from this. So we have a sum over a sub lambda over some frequencies lambda to the s minus a half. The half is just for convenience. So the lambdas are the scalar dimensions shifted by c minus 1 over 12, because this just has support on the heavy spectrum. Right? The first claim is that this converges in the right half plane to the right of sigma equals 1, and admits a meromorphic continuation to the whole complex plane. And the second is that this, after you append a Riemann zeta factor, transforms as an L function. So if we form L by multiplying this zeta function by zeta to the 2s, zeta of 2s rather, then this transforms like a self-dual L function with this gamma factor. So how do you prove this? Well, you prove it by appeal to spectral resolution of SL2Z and the theory of general Dirichlet series. So let me be brief about this. First, the statement is that this quantity curly z is square integrable on the fundamental domain. So why is this true? Well, first of all, unitarity can be shown to imply that the only possible divergence of a primary partition function is at the cusp at infinity. So if I get rid of that divergence, then the remaining thing is going to be square integrable if I subtract enough terms off, right? And so I've constructed this thing to do just that. So we can expand this into some eigenbasis, and the scalar mode of this object takes the following form. There's a constant term which comes from the average over the modular domain, the modular surface, and then some integral over the inner product of this quantity with the non-holomorphic Eisenstein series. Okay. Now, if we insist that this take the form of the scalar mode of a compact CFT when we expand at large y, then that forces the inner product to take this form, a gamma function times the spectral zeta function, where for each term here, you get one of the terms here, and this is just some melanology. Okay. So that's where the zeta function's popping out. So what about the functional equation? Well, the Eisenstein series obeys its own functional equation. That gets inherited here. After some processing, you land on this. Okay. Okay, so this curly z is not the partition function, it's this subtracted thing that is nevertheless preserving compactness. So you might be worried you have to take a difference of two CFT partition functions with the same light spectrum to make this. What if there's just one? But for any partition function, we can construct the corresponding L function in a canonical way by something I'll call J subtraction. Basically, in the Q bar expansion, for every term that has a light state, so a negative power, replace that with a product of modular J functions, both holomorphic and non-holomorphic, and get rid of spurious such terms until you've gotten rid of all the light states. That is, we can define a non-holomorphic Hecke-like operator, which basically takes the form of a finite sum of j's and j bars, if you like, bounded above by sort of the dimension of the state that we're starting with, such that we get rid of all the sort of descendant terms in between, and are just left with something which is q to the minus 1/12 plus some positive power. The minus 1/12 is because then we'll take a primary thing, and there we go. So this fiducial partition function, which is the sort of the thing I started with, and then I make this replacement, enables us to make the desired subtraction while preserving modular invariance, discreteness, and square integrability. Now, square integrability is maybe not a priori obvious, because when you have a term with, say, a positive power of q and a negative power of q bar, it looks like you're introducing a 1 over j factor, and j has a 0 on the unit circle. But every time j of tau is 0, j of tau bar is also 0 because of the special fact that it's on the unit circle. So just to be totally sort of hands-on with this, say you have some term like that, and the j subtraction, you replace it with this, but this is just j times some phase. So you're not introducing new singularities, so you preserve the finiteness property that we need in order for everything to go through. Okay. So to summarize so far, attached to every compact unitary Virasoro CFT is a self-dual degree 4 L function with a universal gamma factor with spectral parameters given here, root number +1, and a simple 0 at the central point, which is something that number theorists often care about. Now, these are not your father's L-functions. These frequencies lambda are not integers, right? We're imagining some sporadic CFT spectrum. And so it's certainly a generalization of what is usually studied. But I think it deserves the name because it shares the main features in common with L-functions, the definition of which is always evolving, and in the first place was slightly arbitrary in any case. OK. So let's talk about some of the features of this thing. So the analytic structure of L is determined by discreteness in the functional equation, and I'll show it to you here. There's only one pole at 1, and there's 3 different types of zeros. Okay, there are trivial zeros, given at half integers starting at a half and moving to the left. There are possible zeta zeros, that is, zeros that this thing can have but need not, at the locations of the zeros of zeta of 2s and zeta of 2 minus 2s. And then there are the non-trivial zeros, which of course are perhaps the most interesting. And unlike a standard L function, I don't currently have an argument that they can't have positive real part moving out arbitrarily far in the complex plane. It's a big open question to study the properties of these non-trivial zeros, but they depend on the theory Z that we're talking about. Okay. And you can derive certain formal results relating the zeros to other properties of this thing. Okay. So let me highlight 2 features of this subtracted high energy density of states, A of lambda. The first is that it vanishes on average. So these trivial poles at these half integers, that is just the statement that the sum of A lambda weighted against integer powers of lambda, positive integer powers, regularized in the sense of the L function, vanishes. So the density of states vanishes on average, which indicates how strong UV-IR relations are in 2D CFT. You fix the light stuff, you subtract off their heavy counterparts, and you're left with something which vanishes on average. Another way to say this, different but related, is that this density exhibits square root cancellation. So the statement that the object we're talking about is regular to the right of s equals 1 is the statement that when you sum up to large frequency, this behaves asymptotically like square root, not like linear in lambda. So you have a square root savings, and this concept, square root cancellation, is central in number theory. Indeed, the Lindelof and Riemann hypotheses are both versions of it applied to different summands, where for the Riemann case, you think about 1 over zeta of s being pole-free to the right of s equals a half. Okay. So the existence of compact irrational CFTs is a miracle of precisely the same type in this short mathematical sense. Okay, so a few comments on the CFT side, then the gravity side, then we move on. So consistency constraints on L of s are acting in high energy states after crossing, if you like, after accounting for the fact that you have the certain low energy states and their sort of modular counterparts at high energies. Now this function knows about the central charge C, but only via the asymptotic level spacings, right? The lambda frequency starts at 0, or just above 0. So C is almost invisible, but not quite. It's hiding in there, and that is suggestive. Now we're heading toward a bootstrap based on the principles of modularity, discreteness, and square integrability, but not unitarity, on the nose, not the full power of unitarity. We're using these other things instead, and discreteness in particular has been difficult to incorporate in bootstrap approaches so far. So recall unitarity guarantees this square integrability, but it's not required for it. And the self-duality of the L function is a statement of the reality of the degeneracies. So we're using reality of the degeneracies, but not positivity in this kind of approach. You can do things for other observables too, just here we're talking about partition function for simplicity. Okay, now on the gravity side, we all know that high energy 2D CFT primaries are dual to black hole microstates in ADS3 quantum gravity. So given some ADS3 EFT at low energies, the statement is that the space of UV completions is the space of these L functions. Whereby space of L functions, that's shorthand for this kind of L function, degree 4 self-dual with this gamma factor and so on. Another way to say this is that the space of black hole microstate spectra that correspond to the frequencies of these L functions, right, that is the space of these L functions as well. That's what it means to UV complete in this spectral language. Now, often in the L-function world, people talk about the zeros, so it seems interesting to think rather than the spectrum of black hole masses, to start thinking about the black hole zeros in quantum gravity. Okay, now, how do properties of 2D CFTs look in the language of L-functions? Here's one example. I'll be brief. So random matrix universality is a property of quantum chaotic systems, including 2D CFTs. And a criterion for a 2D CFT to exhibit random matrix universality in the form of a ramp was recently proposed. And if you translate it to L-function language, it implies that on the critical line, the amplitude of the L-function is bounded above by root t, or t to the 1/2 plus epsilon, where that accounts for possible logs. On the other hand, what is the convexity bound for degree 4 L-functions? It's 1. So random matrix universality of the CFT is subconvexity of this L-function, which I find very appealing. And I just want to emphasize this is different from what people find in relating random matrix theory to subconvexity in the number theory literature, of which there are various types of relations. Here we're inputting it as a physical property of the system and of the frequencies. There they are observing it as a property of the zeros. Interesting. Okay. Now, got about 5 minutes left, and so I want to walk through the proof of this bootstrap bound, and I will be somewhat explicit because it looks rather different than the usual approaches, which of course have not quite been able to prove that bound exactly. So why is this setup well suited for bootstrapping the scalar spectral gap? Well, if the L-function has its first frequency bounded above, then it means that for all but a single possible exceptional spectrum, we have this bound on the scalar primary spectrum, where the single possible exception comes from the fact that we are looking at a difference of partition functions. Of course, a single possible exception to some bound is extremely acceptable. You know, measure 0 would have been fine. One exception, we can more than live with that. Now, what is the state of the art of this subfield at large C? Simeon wrote his paper in 2009 that kicked off the modular bootstrap. It's been Hellermania ever since. And so his bound was C over 6. So this is an upper bound on the lightest non-vacuum primary, here spinless. The best bounds analytically are now here, numerically here. Due to these authors in 2019, there's been a bottleneck. Basically, large C and the truncation procedures in solving the modular bootstrap equations are don't play well. They don't commute. And so C over 12 has long been the horizon for this problem, basically due to the fact that the large black hole threshold in ADS starts there. I say large in case you're worried about small black holes. Even the large black hole threshold starts right there. But L-functions can prove this bound, in particular for a scalar operator, by bounding lambda star. So the idea of the proof, somewhat inspired by standard L-function proofs, is to play two representations of the L-function off each other. The Dirichlet series, which we've discussed, and the Hadamard factorization into its zeros, which in this case, because of the functional equation, takes a nice simple form without exponential factors you might be expecting. Now let's rewrite the zeta function, just pull out the first lambda 1, and so we have some hatted zeta function here. This will be useful in a moment. And so we're going to play these things off each other and constrain the lightest frequency on the right-hand side. Okay. Now taking the log derivative, we have this relation. So minus log lambda 1 plus the log derivative of this hatted zeta function plus some universal function of s here. Okay. Now suppose for a moment that the last two terms were absent. You would just have to solve this. And this equation has to be satisfied pointwise for every s, where these representations both converge, which is the right half plane to the right of 1. But there's no such solution. Something you can show in a few different ways, but it perhaps is clear. Right? The right-hand side is some negative large constant. Here we have to solve this for every s. So the only way this can be solved is if there's some tail of zeros whose magnitude is becoming very large. But you can show that the large lambda, or rather large rho limit of the right-hand side, can't give you a large negative constant with no s dependence. So the strategy is to validate this approximation when we take lambda 1 to scale with c. Okay. So the log derivative is here. Now the hatted zeta function takes this form where I just write it as a sum of two types of terms. And we can show that the derivative in the numerator is bounded uniformly in lambda 1. So HKS is entering here by telling us that the semi-classical tail that extends all the way down to some finite dimension and actually cuts off any possible divergence. So in other words, we can evaluate this piece semi-classically in the so-called square root cancellation regime. You get something finite. And this is just some finite sum. Remember, epsilon is just this finite fixed constant. So the derivative, which just adds a log lambda into here, is bounded uniformly in lambda 1. So as long as we are not parametrically close to a 0, which would make the denominator 0, the log derivative is bounded uniformly, which is to say that S must lie in a zero-free region. That is, S must be such that for all zeros, as lambda 1 goes to infinity, it is not parametrically close to any of them. Right? It's greater than some delta, which is uniformly finite as you take large lambda. Now, if we want to drop this f of s term, s must not be pushed out too far, because f of s grows logarithmically like log s squared. So this approximation is good when s sits in a zero-free region that's not too far away from the origin. In other words, a bootstrap bound follows as long as the L function is not dense with zeros inside a large disk like this, which is a very mild assumption, which you can actually prove is impossible. Why? Well, the Hadamard representation, without giving any details, actually correlates the gap with the number of non-trivial zeros, which is bounded above by the number of non-trivial zeros of Riemann zeta, which famously is dense on a line, but not in a disk. So the number of non-trivial zeros is not nearly enough to fill a disk of the right size, such that you can't find an appropriate zero-free region. And so the bound follows. Now, I'm basically out of time. There's a check here, which is very reassuring. If you look at the Narain case, where the gap grows with n, the proof should break down. It does because the gamma factor depends on n, which is getting large. So this is a reassuring fact about the strategy. There's a speculation here. We ought not to spend our last minute talking about that. So hints of a lattice, well, possibly general irrational CFTs have some lattice structure hiding in their high-energy chaotic spectra. This is just would have been a cryptic comment in any case, but due to time, it will become even more so, because I'm just going to say simply that whereas we expect that the high-energy spectrum should be extremely structureless beyond the constraints required by exhibiting random matrix statistics, I think that is missing something for reasons I will not explain. So, to conclude, we've initiated a structural formulation of 2D CFT in the language of analytic number theory, which I find very striking. And you can imagine a new kind of bootstrap where you pass between the dimensions and the zeros using certain tools that are available, the number theorists are familiar with. And I think it's promising to think more about these directions in the context of gravity and ask questions like, what is the L function of ADS3 pure gravity? So, thanks.
Come on.
Thanks for inspiring talk. So you're connecting aspects of CFT with L functions. So the map one way is clear, CFT to L function. But L function to CFT is less clear. In particular, modular forms, having just a modular partition function is not enough, as we know, for defining a CFT. Why do you think this is enough to get you, or you're just hoping?
No, I'm not just hoping, I'm constructing, but the arrow you articulated is the one we want. In other words, if you take the L functions the mathematicians study now, they ought not to correspond to the spectra of 2D CFTs, which are irrational, chaotic, all the rest, because if you think about their frequencies, they are just integers. So for example, known L functions can give you the CFT L function, if you like, of Narain CFT, but that's because that is undergirded by a lattice.
I mean,
so.
the axioms of CFT, we know that the partition function having a modular structure and so forth is far cry from defining a theory.
Yeah.
We don't expect any modular function necessarily to give you a CFT.
Mm-hmm.
So what aspect, what you feel that this L function captures everything you need for a CFT?
No, I wouldn't say that.
So therefore, how do you know that if I have just the L function properties, you define a CFT?
Well, I wouldn't say you define a CFT. I don't think I said that.
Well, you're mapping the CFT to L function. That's not the case. CFT gives you L function, but not.
I'm saying if you have a CFT, it has a partition function.
Yeah.
And attached to every CFT
right,
is
that's
an L
one-way
function.
map, not the reversible.
That's right, but it's the one I want. Attached to every CFT is an L
Well,
function.
not necessarily, because this might say that there's this gap is a max, but it's not achievable, or is it achievable, etc. with CFT, you wouldn't know.
The spectral gap thing you're talking
Yeah.
about? But the fact, because it's an upper bound, the upper bound is lower than any upper bound we've achieved, so that's what we want to.
But it might give you the impression that there is one, but it's not necessarily the case.
Indeed, perhaps the upper bound is even lower. Yeah, thanks.
Thank you very much. So let me understand if I understood. So let me see if I understood. So you are claiming a proof of the C/12 bound for the modular Bootstrap for purely Virasoro CFTs. Under which assumptions exactly? Could you spell them again?
Yes. That we are taking a large C limit of unitary compact CFT, and there is a unique possible exceptional spectrum which violates this bound.
Sorry, the last point. Can you elaborate the last point?
Sure. Because we are leaning on this difference of partition functions to make this argument, it could be that one of those partition functions has a gap arbitrarily large, but the other one needs to have a state down here. So there can always be one spectrum which violates this bound, but just one.
I see. And you're not assuming implicitly anything about chaotic distribution, or at some point you mentioned the miracle of compact Virasoro CFTs, which is a miracle we haven't actually observed yet because we don't have a single example.
Yeah, I view this as giving us a more rigorous explanation why. Saying that if by observe you mean have one in hand with the spectrum enumerated, this is like this is like saying you have all the Riemann zeta zeros and then some. And this is giving a sharp characterization of why that's hard and why we shouldn't expect to achieve that so explicitly.
Thank you.
Did this imply something for the case with spin, because this was the bound for a scalar operator, or is that more difficult?
Thanks. So yeah, there's some comments one can make about spin, but from this SL2Z perspective, one then needs to start accounting for these mass cusp forms in this spectral decomposition. They can give contribution to the spectrum which the Eisenstein piece can't capture, and so essentially, does this L function tell us about the spinning spectrum? I think it gives us some part of the answer, but I haven't fully thought about that. So I don't immediately have a prediction for what the spinning bound is, say.
Perhaps I missed this, but for the L functions that you define, do you still expect chaos for the zeros of the L
Good
function?
question.
And if so, what does that imply for the CFT?
Yeah, understanding the zeros is an important thing to do. I mean, because the L function is constructible from its zeros, it would be nice to understand where these non-trivial zeros lie. For example, I don't think I have any argument that there must be an infinite set of zeros on the critical line. That would be a reasonable expectation, but one needs to be careful. The first thing to establish would be that there cannot be zeros with arbitrarily large real part. That would be very helpful and allow us to then infer various other things, actually. But that is number one. As for whether they exhibit chaos, well, if they're scattered all over the place, then you need to even characterize which collection of zeros you're talking about, whereas when they're on the critical line, it's much easier to start talking about their distribution, because you just have to talk about the imaginary part, and then you can make a random matrix model of that and match it. So sure, there ought to be some notion of chaos there, but it's unclear to me what that has to do with the chaos and the frequencies, if anything.
All right. Well, unfortunately, we're out of time, so please ask the remaining questions during the break. Let's thank the three speakers again. And we reconvene at 4:45.